I suppose we might want to start with the big discussion. Why the whole debate in the first place now? Why are we talking about propellant generation on the moon?
Well, first of all, pleasure to be here. Well, we're talking about that for many reasons, but the most important reason is that it's a fantastic opportunity for all of the humanity to increase our exploration capabilities. We are very much limited on Earth in space exploration when we depend on Earth. It's very hard to get out of the Earth. It costs a lot of fuel, a lot of money. Every kilogram of mass is just so precious, and 90% of each rocket is fuel. So for the last couple of years, we tried to solve that issue, and we tried to solve that with reusing the rocket component, so the dry component of the rocket, with boosters reusability, and second right now with upper stage reusability with heavy systems by SpaceX. But that's not enough. It still leaves us 90% of non-reusable component that is very crucial for leaving the Earth and for going out to other nodes, other places within the solar system. So that's why the space missions have to be very compact, very lightweight, because we can't simply afford anything else. And even with the most powerful rocket engines, even with the most complex staging systems within our rockets, we still hit that limit. We can't go beyond that. We can't go faster. We can't lift more payload. So it's challenging. And the only thing that
can you think of anything that is not challenging about?
Oh, there's a lot of challenges here. But the only thing that shifts that, the only thing that increases that our efficiency in lifting objects to space and to other places within the solar system is refueling. And that changes the whole equation, that changes the whole situation. We can expand further on because that increases our payload capability, our delta V capability by orders of magnitude. So where do we source fuel in space? And that is a very important question, and that was answered pretty recently, about 10 years ago, by confirming that we have on the moon significant amounts of water ice that we could use potentially to build extraction systems, capture systems, and processing infrastructure that could change it from water vapor, from liquid water to oxygen and hydrogen. And oxygen and hydrogen that are in the liquid form are actually the very primary rocket fuels that are used. They are used, I think, on ULA rockets and Orion rockets. So we use that quite often, and they're pretty powerful. So we have that place where we can source fuel from, and we see that it just brings so much potential for refueling of large space missions, for servicing of satellites that are already on orbit that could increase their longevity. So we have clients for that, we have resource, and now we're developing a technology that we could hopefully successfully use within the next decade or so.
So you're at a stage where you're actually working on the technology itself, not yet the actual infrastructure part that needs to be set up on the moon, but the technical process, the chemical process.
Well, we actually we are trying to solve very basic questions about that. Even
I can just add to this actually. Talking about the whole chemical process of producing this rocket fuel in space. Like Gordon, you were bringing up hydrogen, which you would create from electrolysis with water. Something that's actually very interesting to consider in the context of propellant production in space is that many of these fundamental processes that we need, like for example the electrolysis, and in some cases also methanation reactions on Mars, for example, have been used in industry actually for quite a lot of years. So one of the key challenges in doing this is not so much figuring out from scratch how are we going to do this, because this is already pretty well established actually on Earth. The difficulty is how do we then bring all of this stuff to space? How do we actually get say for hydrogen production and oxygen production, how do we actually get access to the water in space that we need to do this?
And how would you describe this, the current stage where we are at? Obviously, there are a number of bottlenecks to such a complex problem, but where are we? What kind of time frame are we talking about, looking at all the companies who are trying to address this issue?
Well, that's a pretty good question, because it's hard to say. Of course, depends on the development process going forward. But like I just mentioned, say you're producing liquid hydrogen, liquid oxygen, right? Fundamental rocket fuel, like Gordon mentioned. You need to perform some kind of extraction, depending on where you are. Say on the moon, you might be digging out lunar regolith and then processing that. Somehow you need to separate the ice from the moon sand itself. This we can do on Earth already. We can separate materials that we've dug out of the Earth. We've been doing this for hundreds of years. Then once you have the water on its own, which you need in order to produce the hydrogen and the oxygen, you would perform what's known as an electrolysis. You probably all did this in like middle school physics classes, where you have two test tubes and you apply a voltage potential in like small bucket of water. So this technology is actually also pretty well understood. Now that you have the hydrogen and the oxygen at hand, you need to perform some kind of liquefaction. Liquefaction of oxygen here on Earth. You produce oxygen here on Earth by cooling down the air, but in space, when you have the oxygen, you can just like only cool down the oxygen. So actually, you simplify the process of making oxygen to some extent. And hydrogen is a bit of a different beast, because the liquid temperature of hydrogen is around 20 Kelvin. So 20 degrees above absolute zero. So getting to those temperatures is quite difficult. But all of these individual steps are already performed on Earth. The difficulty in doing this is like putting this together in space. So it's really not so much a question of like technology maturity. It's more like a question of when does someone see the funding needed in order to put this in space? Like there has to be some kind of incentive to actually put this in space. There's a lot of talk about producing fuel in space, but let's imagine that tomorrow I have 3 megatons of liquid hydrogen on the moon. Who's going to use it, right?
Rasmus, correct me if I'm wrong, but the way I see it, the biggest challenge seemed to be that all of these individual processes here on Earth are not exactly nanotechnologies. In other words, you need production lines for that. You need major infrastructure, and you need very specific chemical conditions, atmospheric conditions, etc., etc. So essentially what we are talking about is establishing heavy infrastructure necessary on site before we can even start the conversation. Is that the case, or am I missing something?
That's absolutely the case. You need these massive production lines, like what you're saying.
Which, given the price per kilo in space, the transportation price, that itself answers the question why we're not yet there, right?
Right, and then you want to take a step back, like could we even produce the material needed for these things in space, right? Let's say you would just produce the plant itself on the moon from moon material instead of actually shipping the things on Earth. That would be like the next step to this. But no, you're completely right. The cost of bringing a kilogram to space just to low Earth orbit is extremely expensive. But like now going to the moon, you need to add on top of this another margin, because just like Gordon also was mentioning, when you're going to space, 90% of your spacecraft has to be pure fuel, but that's just to get to like approximately orbit around Earth. Then actually getting to the moon now, another good part of your spacecraft has to be just fuel. So by the time you get to the moon, it's only like a very, very, very small fraction of your spacecraft, which is actually your production line. And what you just mentioned, you need these massive production lines to fuel these spacecraft. So no, it's an extremely difficult question, but it's mostly like a logistics challenge, much more than it's like a technological challenge.
So I'm not sure if you had a chance to watch our conversation with Robert Kobani yesterday, where we asked him about the prospect of people coming to Mars and what it will take, the sheer travel period alone, but the actual infrastructure to make sure people survive even for a short period of time on Mars requires bringing all that infrastructure. That brings me to the next question. Rasmus, allow me please to ask Gordon that question first, so we'll have a little more time to think about the answer. Lucky you. So the question is, if that looks like such a remote prospect, why should the respective businesses and institutions you represent be interested in the first place?
That is a great question. And I think we could use a couple of terrestrial examples why we develop very expensive. Critical.
Tomorrow is all about terrestrial, so come back.
But why we develop in the first place very heavy, expensive terrestrial infrastructure? Why do we develop a nuclear power plant that costs tens of billions of dollars?
That's actually quite easy,
and
isn't it?
It pays off after 50 years. Why do we do that? Because it provides you resources to build a business on, that provides you a strategic resource to build infrastructure, to build your life, your economy. So basically,
Gordon, but you will agree that the cost to value ratio here is very different from even building a nuclear power plant.
Not actually. Well, if we look at the thermal mining infrastructure for the moon, so the very basic concept of how we can extract water from the permanently shadowed regions deposits, then we are talking about $2, $3, maybe $4 billion per the infrastructure. And even without...
Just pennies.
Actually, it is, because if you develop that infrastructure to pay it off by selling the rocket propellant to the customers that are very much interested in doing that, because we need to service a lot of satellites, we need to service a lot of space missions, we're actually looking at a break-even in the investment after just a couple of years, and the return on investment, actually quite a significant return on investment in just 10 years. So it's already promising a business case, even without that strategic benefits of inducing economy, of providing a resources for the economy to flourish. So we already have a business case for that, and what we don't have is a will to pay that.
All right, fair enough.
Quite a couple of billions of dollars.
You're talking about the business case and obviously significant amounts of money. So tell me, how would you describe how easy or how challenging is it now? Because I would presume the funding we're talking about is government grants, agency grants, big players. So are we really coming any closer to private investors really thinking about the prospect of return on investment coming in 10 years, and the likability, the probability of it really still quite low?
Yeah, I'll come back to the same argument with the nuclear power plant or a tunnel or a bridge. So how we develop those infrastructures.
You're making it easier from nuclear power plant to tunnel to bridge.
Yeah, but they
hardly same investments, are they?
They cost billions of euro, dollars, whatever. And the model for constructing them is mostly public-private partnerships. So we have a government that funds those enterprises through private contractors, and that's actually the era in the space industry right now. We have government agencies that fund a bunch of different contractors, small and medium enterprises like Astronika or larger integrators to develop those systems. And we have a lot of examples in the space industry where the space industry actually develops those systems quite well, and at a lower cost, quicker. SpaceX developed Falcon Heavy and Falcon system, and now the Super Heavy way faster than the SLS by NASA. So you're shifting the risk, and you're shifting basically you're shifting the risk on private contractors, so they take it on themselves, but they actually are quite well with spending their money and spending those resources. So we have a good business model for developing that. We need a political will to actually say that, well, there's an agency or there's a customer that says right now we're going to buy 500 tons or 100 tons of rocket propellant in 10 years. We're going to pay this and this amount of money for it. And if is there anyone out there that takes that challenge on themselves? Well, there's definitely a couple of people that will do that. I mean, the first space resources contract that we just recently seen, it was a contract granted by NASA to Lunar Outpost, who said that they're going to extract regolith from the lunar ground by the rover for just $1 per that bulk regolith. So that was the first very symbolical contract. And we also, within the last couple of months, we've seen the first actual production of resource in space by Perseverance and Moxie, who first produced oxygen on another planet, on another solar system body. So we're getting there. We have a lot of significant knowledge gaps about the regolith, about those resources, about those deposits right now, and that's why NASA CLIPS and other programs are trying to address that with prospecting. But
Gordon, let me make it
there.
a little bit more tougher for you.
Yeah.
Of all the things you could be doing about space-related technologies, why would you be especially interested in the propellant technologies, given the complexities you have just explained? I mean, you have a lot of choice, and you're doing quite a lot of other things as well.
I mean, supply chains are complex. Supply chains are complex, but they are fueling our economy. The construction of a highway with gas stations may be complex, but we need that to get from point A to point B sustainably. So we need those critical infrastructure, orbital infrastructure, lunar outposts to explore space sustainably. So sustainability here is the key. And that actually also induces new economy, new space economy, and it's not a new concept actually. It was dwelled into in the Apollo times, and it just recently came back online. But yeah, we do that because we have this drive for space. I mean, we just want to be in space, and there's a lot of riches out there that we can explore and develop, that we can enrich ourselves with.
Gordon, what you've just said reminded me of an anecdote I overheard this morning accidentally at the Mars Yard, because you could see like almost 100 kids there asking their parents different questions about the rovers in the Mars Yard, but there was also an elderly person with a bike, and he looked at the Mars Yard, he looked at the rover, and he said something like that. And he said, so they can already solve problems in space, but they haven't solved the ones on Earth yet. So that's also a perspective, isn't it?
It's a recurring argument about this space industry in itself, space exploration. So,
exactly.
Yeah.
Let's go back to Rasmus. Rasmus, you've had quite some time to think about the answer. Why would the institution, the business you represent in, be interested in propellants?
In propellants, just the propellants, like the what fuels the rocket,
and everything linked to it, of course. Yeah.
I mean, it's key. I mean, the thing with rockets as a mode of transportation compared to like regular vehicles, like how you would have planes or trucks or boats, ships here on Earth, is that rockets really don't need a medium to travel in. So for example, you for a boat you need water, for a plane you need some kind of atmosphere, for a truck you need some ground to drive on. And when you start messing with physics in this way, it just becomes very expensive, because there's some energy that you need to pay, and you need to find this in the propellant. And all of the things you guys have just been talking about, like doing stuff in space, is going to require a huge amount of logistics, like we were all also talking about just before, which entails moving like lots of mass around in space, which down the line means we're going to need a lot of propellant. We're going to need a lot of rocket fuel to do this, and until someone comes up with a much better idea than like expulsion-based transportation in space, then we're kind of really just stuck where we are now. So any kind of process or any kind of research that dives into how can we maybe spend less rocket fuel doing the same stuff? How can we maybe make rocket fuel cheaper? How can we make it, on Earth, how can we make it greener? There's, of course, quite a lot of, like you produce a bunch of CO2 and other molecules in the combustion of rocket fuel. Like any kind of progress that tries to address one of those questions I just asked is interesting, because just like with technology and innovation, you're going to be wanting to drive things forward. So, and that's really where it is going forward with propellant, right? Because rockets and rocket fuels have been a thing for hundreds and hundreds of years now. I think the Chinese were the first to use it as unfortunately, as a military thing back in the 13th century or something like that.
Rasmus, tell me,
it's old technology.
Tell me, it's obviously a hugely interesting topic in itself, but tell me, do you think there's a probability of some kind of disruptive innovation happening, in the sense that we are still thinking about combustible technologies, not in space, of course, but here on Earth to a large extent? There is some talk about nuclear-powered rockets, which might actually prove to be the future. We've heard of electric versions of it and thermal versions of it being properly researched. We hear some about it, but do you think there's a probability, just like in the world of batteries? Of course, we're working on traditional lithium-ion batteries, but at the same time, you hear of solid-state batteries, which might actually reverse the whole market, change it entirely. So, is it likely that in the next 5 to 10 years we'll see a completely new technology? Do you think there are any signs of that happening now for propellants?
So I think that's a great question. So like, just before I jump onto that, you need to ask yourself, what is a rocket engine? And a rocket engine is really just a device which throws out mass in the other direction of the direction you want to go. So any kind of system which does that has the potential to change the propulsion industry and the space transportation industry. Really, what it all boils down to is how many kilograms do I need to throw away in order for me to produce some amount of thrust? And people have been exploring different ways of doing this for a very long time. And chemical rocket engines, like what we see everywhere today for putting things in space, is a very, at least on a high level, a very well understood area. So within chemical rocket engines, there are some signs of like progress that might happen in the future. There's something called rotary detonation engines, which are extremely complex compared to the normal counterparts. But another one, like what you mentioned, is the nuclear technology, right? Where you're not really relying on a combustion anymore. You're just relying on another way to generate energy. I think definitely could have a chance. NASA abandoned their own nuclear project many years ago for, I think, largely political reasons, and largely because NASA stopped getting funding after they landed on the moon. At least they started receiving less and less. But for sure, I think there are some technologies out there which haven't been explored, which I hope to see be explored in the coming years now that the space sector is becoming more and more privatized.
Rasmus, you've just provoked me asking this question, the question of the famous or notorious space isotope that we know of since at least the 60s in the Apollo program. We're talking obviously about helium-3. What's happening about it? Because this could technically, rumor has it we are running out of this resource here on Earth. There's a lot of it on the moon. So is this one of the directions do you think will be the future? Gordon and Rasmus, how do you think?
So I'll try to answer that. Well, there are significant amounts of helium-3 on the moon. I mean, significant relative to Earth, but we're still talking about parts per million, parts per billion in each regolith, bulk regolith mass or volume. So we need to extract and process hundreds of thousands of tons of regolith to have
brings
meaningful...
us back to a production line on the moon.
Yeah, so we need to develop those heavy machinery, heavy infrastructure for it to actually go forward with it. And so I think we're quite a long way to go with that, but that's definitely something for the future and prior development in technology for regolith excavation and for ice excavation would definitely help scale it up to the scales that we needed in helium-3. And I think by that time we might be able to develop those fusion reactors on Earth that we could actually fuel them with that resource. So yeah, I think there's a quite a good roadmap for it for the next couple of decades.
Gentlemen, it's absolutely fascinating to talk to you. In the closing sentence for both of you, I would like to kindly ask you to say something that would send our ERC audience to an interesting reference point or a website or study materials that they should read about, be familiar with in that context. Maybe what Astronika is doing, for instance.
Yeah, definitely check out our webpage. But for space resources, repository knowledge, you should definitely check Space Resources Roundtable conference webpage. So there's this conference every year that there's great presentations about the recent developments in space resources technologies, business model, things like that. And they have a repository. You can read anything from the last 20 years that they developed. So yeah, you should check on that.
Thank you very much, Gordon. Rasmus?
The Mars Society recently, a couple of years ago, they played a big role, I believe, in a huge study which was conducted on the conditions on Mars and how they would allow people to live on Mars. And it's a 100-page study where they went through like everything from like cell biology to fuel production. You can find this by Googling SR-SAG2. I actually don't remember the full name for it. I just remember reading it, I think, a year or so ago, and I was blown back by the amount of detail they covered in this. So I would definitely encourage anybody who's interested in the colonization of space to just read all of this, no matter if like they understand the technical facets of this, because they cover everything. They go through biology, they go through propellant production, everything in between.
Absolutely fantastic recommendations from both of you. Thank you for joining us here at ERC, remotely, Rasmus, and here on site, Gordon. Thank you, gentlemen. It's been a pleasure to talk to you.
Pleasure. Thank you.
Pleasure. Thanks.